So I've got up there the square root of 13, which you could easily type into your calculator and get an answer for. It'll be a little bigger than 3, because 3 squared is 9, and a little less than 4, because 4 squared is 16. So we're somewhere in the 3.5-ish range. But it would be nice to have an exact number, so you launch directly to your calculator and you type in root 13, and through the magic of whatever it does, it spits out an exact number for you. But have you ever wondered, how exactly does your calculator do that? Because if it's just memory recall, then someone would have had to have stored all of the possible inputs for a radical and have them saved on your calculator. And that's just unrealistic because, after all, there are an infinite number of numbers, so the square root of an infinite number of numbers would require an infinite number of storage points, which would require an infinite amount of memory on your calculator. And that's just impractical. So there must be a way for your calculator to accept an input and then hack through a process using its processing power in order to take a bad guess, get a better guess, get a better guess, get a better guess, and eventually refine it down to the answer that we want. So the algorithm that it uses actually is called Newton's method, and Newton as in Isaac Newton, as in 1670 something or other. So way back when the human race was trying to figure out that you should not burn witches, this cat was sitting down trying to figure out how to get the square root of 13, which in a way was witchcraft at the time. So fortunately math was the one bit of sorcery that was not punishable by combustion. So how do you do that? Well, the trick lies in the fact that if some number equals the square root of 13, then if you take that number and square it, you get 13. If you took this 13 and brought it to the other side, you would have x squared minus 13 equals 0. And what you have here is the setup for finding the x-intercepts of some function like this. So you see, if I were trying to find the x-intercepts of x squared subtract 13, I would replace the function with 0, and then I would kick the 13 over, and then I'd square root it, and my calculator would spit that out. But if I'm in the aforementioned witch hunting times of 1670 or so, and I don't have a calculator for another 400 years, how am I going to solve this? Well, if I can draw you a picture and get an x-axis, no, that's a y-axis, and an x-axis. This function here is just a parabola, and it's a parabola that has been shifted down 13 squares. So its vertex is sitting on the y-axis at negative 13, and then it does this. And as we mentioned, it's falling somewhere between 3 and 4. Okay, so I'm going to take a really bad guess. I'm going to guess 3 to start. So guess that the the square root of 13 is 3, which is wrong. Which we know is wrong. But not too wrong. Okay, good. So I'm going to guess 3. What I'm going to do then is I'm going to go to the function and I'm going to find the value of this function at 3. So the parabola I'm working with at 3 9 minus 13 is 9 minus 4. Okay. If I had picked the right number, that would be 0. So I'm confirming that this is in fact wrong. I'm also going to take the derivative of this thing. So df dx would be 2x. That's easy. And I'm going to evaluate that derivative when x equals 3. So that would be 2 times 3 gives me 6. All right. So now that I have those numbers, I can write the equation of a line that is tangent to this parabola at that place. So all lines are y equals mx plus b. I have a y value at that place, it's negative 4. I have a slope at that place, it's 6. I have an x value at that place, it's 3. That was my bad guess. I just need the y-intercept. So negative 4, 6 times 3 is 18, plus b. Kick that over. Negative 4 subtract 18 would be negative 22. Okay? So the equation at that place would be y equals 6x subtract 22. Okay, so how does that help me? Well, this line does this. Do you notice that this value, this place where my tangent line crosses the x-axis, is a little closer to the true value of the square root of 13? So I could take a bad guess, generate a tangent, and then find the x-intercept of that tangent, and it should give me a better guess. So I'm going to do that. Get the y-intercept, or the x-intercept of that. So I'd have to set this to 0. Be 6x minus 22. Kick that over. Divide by 6. 22 divided by 6 is 3.66666, etc. Okay. So I'm going to decide how many decimals I want to refine this down to. So I'm going to go with to 5 decimal places. Okay, so I guessed 3, which I knew was wrong. I found a tangent at that place and rode that tangent back to the x-axis. And the place that I got there was a little better guess for what the square root of 13 was. So I'm going to take this new guess and I'm going to pop it up here. 0.666. And because I'm trying to be accurate to 5 decimal places, I need to keep those 5 decimal places and one more. And I can round it off at that place. So that would be 3.66667 if I round her up. Okay, so I'm going to erase this stuff, and I'm going to take my new guess, and I'm going to run it through the same process. So first off, I need the function at 3.66667. So I would get that by taking this number and squaring it. So 3.66667 squared minus 13 gives me 0.444444. Keep the 5 decimal places that I want and one more. All right, the derivative at that place, 5, 6, would be 2 times that value. 7.3333334. Okay, so my tangent then, y equals mx plus b, is going to be the y value of this. 2, 3, 4, 5, 6 fours equals the slope 7.33334. The x value 3.66667 plus b. So I need to get my y-intercept. That will be 1, 2, 3, 4, 5, 6 fours. Subtract 7.333334 times 3.666667, which gives me negative 26.444444. 1, 2, 3, 4. That's 5 fours and a 9, which is going to round this up to 50. Okay, so my tangent then is y equals 7.33334x minus 26.44450. So that's my new tangent. I'm going to ride that one back to the x-axis by finding its x-intercept. So 0 equals this. 334x minus 26.4444450. Kick this over. Never fear, we're going to shorten this up real quick so that you don't have to write all this over and over and over again. That number divided by 7.333334 gives me 3.606. 3.606061. So 1, 2, 3, 4, 5. Those are the 5 decimals I wanted, and one more. Okay, so do you notice that my first guess was 3? My next guess was 3.6666667, and my next guess after that was 3.6 with a 0 here. Do you notice that we're sort of spiraling around a particular value, this 3.5-ish range? So I'm going to repeat this process. I'm going to try and speed it up a little bit without writing down quite all the decimals. But what have we got here? My old guess kept the 3, kept the 6, replaced this with a 0, replaced this with a 0, and replaced this with a 1. Okay, so I need to go through and I need to work this out. I'm going to change this. Instead of writing the number over and over again, I'm going to write function at the new guess. I'm going to write that here too, at the new guess. Okay, so in order to get the function at this number, I have to take this number and stick it here. So 3.606061 squared, subtract 13, gives me, goodness, 0.00367. 1, 2, 3, 4, 5 decimal places. The next one is a 9 and it rounds down. Keep that. 3.60661 times 2 in order to do the derivative is 7.21212. Okay, Now, if I look at this mess, what did I end up doing here? In order to get the y-intercept, I always ended up taking my y value, and I ended up subtracting this slope times the x value. So to get this, I'm going to do 0.003679 subtract 7.212122 multiplied by 3.606061. Give you a second to think about that. Actually, maybe I'll write it down. I hope in your head that you're trying to think about how we could move these equations around in order to speed this process up. So my y value is this. My x value was this. And my slope was this. Okay. Which gives me a new b value. So 0.003679 subtract 7.212122 multiplied by 3.606061 gives me negative 26.003673. 1, 2, 3, 4, 5 digits I want, plus 1 extra. Okay. Set that to 0. This number goes here. I'm not going to write it again. In order to get the new guess, this is going to come over to the other side, and I'm going to divide by my slope. So my new guess would be that number divided by 7.33. Nope, that's not my slope. That's my slope there. So 26.003673 divided by 7.212122 gives me 3.60555. It's 1, 2, 3, 4, 5 digits I want. The next one is a 0, but there's a 9 after it, so it rounds up to that. Okay, so do you notice that in this guess to this guess, I have kept the 3, I've kept the 6, I've kept the 0, and this 6 here dropped just a little bit. Okay. Now, I would like to speed this process up a little bit, so we're going to try and make this go a little faster. So first off, what did I do? I took this thing and I made it my guess. So I'm going to call that A. Call my guess A. So I took the function at A and I got the derivative at A. And once I had those things, I plugged them into the equation for a line. So my y value then is the function at my guess. M is the slope at my guess. X was my guess. And I needed a y-intercept. So when I was running through this, this was a number, this was a number, and this was a number. So this was the only thing I had to solve for. So I'm going to kick this stuff over there. I'd end up with my y-intercept being the function at my guess, subtract, and I'm just going to reverse the order of these things because it's easier to read. My guess multiplied by the derivative evaluated at my guess. Okay. Then I took my new y-intercept and I plugged it into the generic equation of a line, mx plus b. My slope, though, was this thing, df dx evaluated at my guess. X values, I was trying to solve that later. My y-intercept is this hot mess here, f of a minus a df dx for a, and I'm sure you're having a panic attack looking at all these symbols, but don't worry, it's going to get better. The next thing I did once I had my tangent was I set this equal to 0 because I was trying to find the x-intercepts of this line. And this thing sitting here, that's my new guess. So I want it to say x equals. So I'm going to have to move some stuff. I'm going to move this over. So I'll have df by dx at x equals a x equals this thing, if it comes over, would become positive. And this thing would become negative. Right. And now, in order to get this to say x equals, I'm going to have to divide by this. Well, you notice that that exact thing is sitting here. So this divided by this goes away and leaves me with only a. And this thing would be the function at a divided by the derivative at a. Now that's all smooshed up, but I'll write it up here for you in a minute. This thing then is supposed to give me my next guess, which I'm going to call b. Alright, so I'm going to erase this a little bit, and then we'll write it up there so you can see a little more clearly what that says. It says that my next guess is my first guess subtracted by the function evaluated at my first guess divided by the derivative evaluated at my first guess. Okay. So if I take this particular function that I'm working on, right, the function evaluated at a, so for this example, my next guess will be my first guess subtract my first guess squared minus 13 divided by 2 times my first guess. So this is a little algorithm that's going to let me get through this a little bit faster. So if a is this 3.605551, then I would get b by taking this number and squaring it, subtracting 13, divide by 2, divide by that number, and then subtract it from the guess I had at the beginning. Think about that for a minute. Okay, so 3.605551 squared. Subtract 13 gives me something in the 10 to the negative 6. Divide by 2. Divide by 3.605551 equals. And then I'm going to subtract that. So I'm going to take 3.605551, subtract the answer I got from that mess, and I get 3.605551. And there's some more stuff after it, but we decided at the beginning we were going to go to 5 decimal places. So 1, 2, 3, 4, 5. Do you notice that there is no change? So I guessed 3, and it was wrong. But that gave me something that was closer. It gave me 3.66666, which was wrong. It was my second iteration. So I tried it again through this process, and I got 3.606. That was my third guess, and that was also wrong. Then I ran it through a fourth time, got 3.605551, and when I ran it through the fifth to confirm, my fourth iteration and my fifth iteration matched to the number of decimal places I wanted. So I can say that the square root of 13 to 5 decimal places is 3.605551. So we can test this 2 ways. 3.605551 squared. If I'm right, that should be 13. So 3.605551 squared is 12.999999801. So I am close to 13. 1, 2, 3, 4, 5, 6. I am 2 micro units away from 13. That's pretty close. Second way to check it, actually take the square root of 13. Square root of 13 gives me 3.605551. Look at that. 275. ... So up to that point, right, I clipped her off, I did some rounding, but I was able to evaluate the square root of 13 using this approximation. So this approximating method is called Newton's method, where you take a bad guess and you run it through an algorithm to make it work out. This is what your calculator does. You put in a number, right? It says, I want to know the square root of 13. And preserved in the calculator's memory, in its circuits, is this little algorithm set up like this. So it knows to take the number you put in, square it, you put a number in, 13. Your calculator is programmed to take some random number like 5. Take 5, square it, subtract the number you entered for the square root, divide by 2, divide by that random number it picked, 5, get an answer, subtract it from 5, and that will give it a better guess. Then it takes its better guess, squares it, subtracts the number that you put in, divides by 2, divides by the number it got in the last iteration, subtracts it from the number it got in the last iteration, and has a better guess. And then it does it again, and then it does it again, and then it does it again. And because it's using silicon processors, it can execute this little operation 1,000 times in a millisecond. And so after 1,000 iterations, it has produced to you, it shows you 10 digits of that answer, and then it has stored in its memory hundreds of digits. So it's got more information in there than you can actually see. And it's good enough for what we're doing. So your calculator never actually gives you an answer. It gives you an approximate answer, because that's how computers work, right? They crank out these repetitive calculations at lightning fast speeds so that they can do really good, really precise approximations to answers to whatever number of decimals we feel is necessary based on the activity we're up to. Whew. All right, so we're going to do this one more time, and we're going to start with this algorithm so that you can see how quickly it goes once you've got the formula sitting in front of you. All right, I would like to calculate the square root of 30 to 6 decimal places. Okay, so if the number I'm after is the square root of 30, then that number squared is 30. That number squared minus 30 equals 0 looks like finding the x-intercepts of this particular function. And the derivative of that particular function would be 2x. So if I plunk this function and that derivative into this equation, I end up with my next guess is my first guess subtract my first guess squared minus 30 divided by 2 times my first guess. So we need a place to start. I can tell you that 5 squared is 25 and 6 squared is 36. So this was too small, this was too big. We need a number between 5 and 6. How about 5.5? Question mark, that might not be so bad. So I'm going to make my first guess 5.5. Now I'm only going to write this down for the first one because I don't want to waste your time watching me write down decimal points. But in order to fill this out, my new guess would be my first guess, subtract my first guess squared, subtract 30, divided by 2 times my first guess. So if I run that through a calculator, .5 squared subtract 30 is 0.25. 0.25 divided by 2 divided by 5.5 equals, and then 5.5 subtract that answer gives me 5.477. Put my marker away. 4772. 727272. So I filled up my calculator screen, but I've decided I want it to be accurate to 6 decimal places. So I need to keep 1, 2, 3, 4, 5, 6 decimal places plus 1 more. I can scrap the rest of these. In order to get my next guess, C, I'm going to take this number, put it here and here. So square this, subtract 30, divide by 2, divide by this number, get an answer, and subtract it from that value according to this algorithm, and that should spit out my next guess. So if I take 5.4772727, square it, because I need to square, subtract 30, gives me some tiny decimal, divide by 2, divide by 5.477272 equals, and then take 5.4772727 and subtract that answer. I get 5.477225575, and I'm supposed to keep 1, 2, 3, 4, 5, 6 decimals plus 1 more. Round that up to this 5.4772256. Okay, now the neat part is your calculator probably has an answer button in there. So if you are really good at using one of these things, you could do bracket answer squared minus 30. Apparently I'm not good at using the calculator. Divide by 2. Put that in brackets. Times the answer. And if I go back to the beginning of this little expression, I take the answer I just got and subtract whatever I got there and run it. My next guess is 5.477225575. So keeping 6 decimal places, 1, 2, 3, 4, 5, 6, 7, scrapping these, rounding up, I get identical results. Okay. So the square root of 30 should be somewhere around there, and if I were to check it with a calculator, square root of 30 gives me 5.477225575. That's all the decimals that my screen shows me. So I was able to get exactly that, or whatever my calculator shows me, using this Newton's method. And it was reasonably painless, right? I took one guess, and then I had to run the algorithm once, twice, 3 times, and I was accurate to 6 decimal places. That's pretty good. So you may be wondering, why am I bothering to do this? Because I still use the calculator to do all this crap. Well, if you were Isaac Newton in 1670, you couldn't use your calculator at all, but you could do 5.5 times 5.5, right? Like this. Remember doing that? in elementary school. And you could have done this. Gross. But you could do it. And that's sort of the neat part about this, is it took what is otherwise an impossible calculation and rendered it down into multiplications, subtractions, and divisions. And so if you can take a complicated function like square root, and turn it into the basic calculator functions, then you should probably be able to do this to any function. And that's where this gets interesting, is that sometimes there are functions that you can't work out with algebra because they don't factor, or you have something silly like x equals sine. Well, there's no operator, right? There's no anti-function to break x and sine x. So you're left with having to approximate it. And we've got this tool sitting here that should work on any function as long as I can take its derivative. So I'm going to clean this off, and we're going to try doing x-intercepts of a polynomial that doesn't factor. Okay, so I have this cubic up here. And the first thing that you attempted to do whenever you were sketching a cubic was to try and factor it. And in order to get a number or a factor to divide out with polynomial long division, you had to guess and check numbers that actually went into that cleanly. And they may exist, but they probably don't. So immediately, you've got this function that is defying regular algebra, right? Unless you can find one good clean root, then there's nothing you can do with this. So we're going to have to launch into some sort of approximation. So I'm going to try and get the x-intercepts of this, x-intercepts, to 3 decimal places. I mean, that's good enough for our exercise here. So I've got this Newton's method here. In order to do Newton's method, I need to have the function and I need to have the derivative. So I'm going to have to take the derivative of this. df by dx is 24x squared plus 8x minus 34, and then this term drops out. Okay. So the next thing I'm going to need is a guess. So what to do about that? Well, this function is a cubic. It does something like that. I have a derivative that's quadratic, so I could plunk that into the quadratic formula, and I could find the location of this spot, and I could find the location of that spot. And if the x-axis goes through here, that will give me a place where I can start hunting for those x-intercepts. So let's see, max-mins. See if you remember anything from the curve sketching unit. Happen when the function's derivative equals 0. It's 8x minus 34. All of those numbers divide by 2, so I'm going to scalar down. Divided by 2 is 17. So my max-mins should happen at -4 plus or minus the square root of 4 squared minus 2 times 12 times -17, all divided by 2 times the a value, which is 12. So -4 plus or minus the square root of 16 plus 2 times 12 times 17 gives me 424. Now you can cross your fingers that that's a perfect square, but I have low expectations. It is not. -4 plus or minus 20.591. Now we've already decided that 3 decimals is the level of accuracy we're going to, so that's what I'm going to keep. Divided by 24. So one of these is at -4 plus 20.591 divided by 24, which gives me 0.691, or the other one is the negative case, so negative 4 subtract 20.591 divided by 24 gives me negative 1.025. As with all max mins, I need to get the y value that goes with it. So I'm going to take 0.691 and I'm going to put it up into here. So 8 times 0.691 cubed plus 4 times 0.691 squared. No, you don't. Plus 4 times 0.691 squared minus 34 times 0.691. This calculator is being difficult. Okay, let's try that again. So after all that, I end up with at 0.691, which is going to be this one. 0.691 on the x-axis, negative 3.9495, which rounds up to 3.950. Okay, and if I try this one, negative 4 subtracts 20.591 divided by 24 equals, so 8 times that answer cubed plus 4 times that answer squared minus 34 times that answer plus 15 gives me, goodness, this one up here is at negative 1.025 comma 45.431. All right, so we have 3 x-intercepts to solve here. One of them is here. And that number is somewhere beyond negative 1.025. So I'm going to guess negative 2. That's not a good guess, it's just a number that's past that. One of these x-intercepts is out here. And so that's a number past 0.691. So I'm going to guess 1. This third x-intercept is somewhere between 0.691 and negative 1.025. So I'm going to guess 0. And that'll do. So we're going to have to do this 3 times. So just to be clear, notice that this one is negative, this y value is negative, and this one is positive. So in order for it to do this, it has to cross the x-axis 3 times. So now that I know that, now that I'm hunting for 3 different x-intercepts, I'm going to have to do this process 3 times. I need a guess that is past this maximum, I need a guess that is past this minimum, and I need a guess that lands in between them. So I'm going to start with this one on the end and do my initial guess of negative 2. So my next guess will be negative 2 subtract the function at negative 2 divided by the derivative at -2. So my new guess will be clear 0, subtract 2. Will be 8 times my answer cubed plus 4 times my answer squared minus 34 times -2 plus 15 gives me 35. Okay, 35. My derivative at that place, 0 subtract 2, be 24 times my answer squared plus 8 times my answer minus 34, be 46. So I plugged -2 into the function and got 35. I plugged -2 into the derivative and got 46. So my new guess then will be -2 subtract 35 divided by 46. And I get -2.7608, which rounds up to the 3 decimals I want, and the 8 has a 6 after it, so it rounds up to this number. Great, so to get my new guess, I'm going to take -2.7609, and I'm going to subtract from it the function evaluated at that, so I'm going to have to do 8 times my answer cubed plus 4 times my answer squared. I almost said a bad word. Getting tired of this calculator. Alright, gives me -28.9965. And if I put this number into the derivative, uh, 24 times that number squared plus 8 times that number plus 8 times that number minus 34 gives me 126.8545. So that in the denominator times -28.9965 equals, and then -2.7609, subtract that, gives me -2.5323. So my next guess, we're going to have to take that answer, plop it into my function. So 8 times that answer cubed plus 4 times that answer squared minus 34 times that answer plus 15 gives me -3.16140. That's my 3 decimal places plus 1 extra number. And my last guess, which was 2.5323, put that into the derivative, 24 times that answer squared plus 8 times that answer minus 34 gives me 99.6426. Now, if you take a look at what's happened, do you notice that this number went from 35 to 28, and then all of a sudden it dropped from 28 to 3? But this denominator didn't change very much. My correction factor at the back of this is going to be teeny tiny. That's encouraging. So take that 99, Parker in the denominator, times negative 3.1614, and then take my old guess of negative 2.5323 and subtract my new correction factor. I get negative 2.5006 if I round that. So I kept the 2, I kept the 5, and then some business started happening down here. So I'm going to have to do one more guess at least. 006. So park this number into the function like we've done 8 times already. 8 times the answer cubed plus 4 times the answer squared minus 34 times the answer plus 15 gives me negative 0.05499. And if I take this number and put it into the derivative, (24) times that answer squared plus 8 times that answer minus 34 is 96.0672. Again, look at what happened to this number in the numerator. It's now in the hundredths position, but the denominator is in the hundreds. So a 10 to the negative 2 divided by a 10 to the 2 is a 10 to the negative 4. We're going to be adjusting this last digit back here. So park that thing in the denominator times negative 0.05499. Take my last guess, which is negative 2.5006, and subtract that answer. Gives me negative 2.5000. Alright, now I've got an error there, right? Like I don't have quite a match in my 4th digit, but I'm good to 3 digits. So I'm going to do one more iteration just to be sure. So 8 times 2.5, negative 2.5. 8 times that answer cubed plus 4 times that answer squared minus 34 times that answer plus 15 gives me, boom, nothing. And it doesn't matter what this number is. 0 divided by nothing is 0. 2.5 minus 0 gives me negative 2.5000, which gives me a match. So after a few calculations, I figured out that this x-intercept here is located at negative 2.500 on the x and 0 on the y. Alright, so to 3 decimal points, I have determined where that x-intercept is, and I would never have guessed that value while trying to hunt and peck for my x-intercepts. So I'm going to leave you to do this as an exercise to find this x-intercept and that x-intercept, and then you should be able to go through and sketch this cubic once you have all the appropriate features. Before I leave you, there's one more example I'd like to do where this becomes super practical in a finance kind of context. So this particular equation was used in your grade 11 class when you were trying to calculate the amount of money you would have in an account if you put a certain amount in every week for a certain number of weeks at a particular interest rate. So you did a number of these questions where it would ask you something like, put $100 into an account paying 5% per year for 10 years and tell me what you've got at the end. Well, okay, that's fine. Or you could have done a calculation where it was, I want $10 million. I'm going to tell you the interest rate, and I'm going to tell you how long to leave it. Tell me how much you have to invest. Well, that's fine as well. You could even do a calculation where you did n, where you're trying to find out how long you'd have to make those payments in order to amass that amount of money. But you never once calculated the interest rate. And if I can take a minute to rearrange this to show you, if I pop this I up here, I get this. And if I throw the p into the bracket, p times this, that, I would get something like this. Well, that's a polynomial, and it's a polynomial to the nth power. So that's problematic because unless this n is 2, you couldn't use quadratic formula on it, and quadratic formula was the only tool you had up until this point. But now that we've got Newton's method, we can actually find the places where this expression equals 0. So I'm going to propose a little finance question here. I'm going to ask if you had $100 per pay. That's 26 per year. And we did that for 40 years. Now, that seems like a long time to you, I'm sure, but by the time you have $100 extra a week to start making investments, you're probably 25, and you are likely going to retire sometime around 65, so that's 40 years. Now, 26 payments per year times 40 years gives me, I worked this out ahead of time, 1,040 payments. And it'd be real nice to retire with $10 million in the bank. That'd be great. So, the real question then is, if that's how much I know how I can afford, and that's how long I know I'm going to be investing it for, and that's the amount of money I know I want to have at the end, the only thing left in this equation is the interest rate. So, and that's the critical question though. You know what you know? How much you can afford per pay to save. You also know how long you're going to save for, and you also know how much money you want at the end. Hunting for an interest rate then, going to a bank and saying, I need you to pay me this much interest, or I need to find an investment portfolio that pays me this much interest. That's how these questions actually work, right? Like, I need to shop around to see if I can find the appropriate interest rate. But you have never been able to actually calculate the value of I until today. So we're going to put these numbers into that equation and see what we get. So I would end up with 0 equals, my payment is 100. I don't know my interest rate, but I know I'm putting it in for 1,040 bi-weekly payments. I know I want to get $10 million out at the end, and I've got a payment of 100. So all three of these numbers divide by 100, so I get 1 plus I, 1040, minus, take 2 zeros off that, I'm down to 100,000, and 100 divided by 100 is 1. So if this function is set to 0, I'm really trying to find the x or the I intercepts of some sort of function, let's go m, because we don't use m very much, of I. So if I'm going to do that, my function then, m of I, is 1 plus I to the 1040 minus 100,000. Yep, 100,000 I, subtract 1, clear up some space. Now in order to use Newton's method, I need to take the derivative of that thing. So I have a choice. I could either expand this bracket to the exponent 1040, which would be the biggest and most obnoxious foiling that you've ever tried. Or we could just use some chain rule. So dm by di equals, bring the exponent in front, 1 plus I, drop the exponent by 1. The derivative of this term would be, the derivative of 1 plus I would just be 1, so I don't need to worry about it. Derivative of this is 100,000. The I has gone away, and my negative 1 has vanished. Okay, so my Newton's method then, my next guess would be, my first guess, subtract this number here, 1 plus I to the 1040 minus 100,000 I minus 1 over 1040 1 plus I to the 1039 minus 100,000. Okay, so let's take a guess. 10%, maybe? Now the way this interest rate works, this thing's going to kick out the interest rate I get per payment. So that's 26 a year. So if I round our guess up, let's call it 13% over 26 pays would be 0.5%, which ends up being 0.005. So that's going to be my first guess. Somewhere around 13% interest per year, which works out to 0.5% per pay. So in it goes. A will be, my new guess will be 0.005 minus, and I'm not going to fill it in, I'm just going to type it in, 1 plus 0.005 to the exponent 1040 equals, subtract 100,000 times 0.005 equals, subtract 1 equals negative 322.061. How many decimals we're going to keep? 3? Let's keep 3. So 1, 2, 3 plus an extra. There we go. The denominator would be 1.005 to the exponent 1039 times 1040 minus 100,000 gives me 85170.3742. Okay, now that is much smaller than this, so I'm expecting a very small correction factor. So put that in the denominator, multiply it by negative 322.0613. Take my guess of 0.005 and subtract that answer, and I get 0.0087. Okay. Now, if I were doing scientific notation, that's where my significant digits would start. So I'm going to keep 3 decimals after that. 8.7814. Okay. So my next guess will be 0.00878114. Subtract. I'm going to put this number into the numerator. 1.00878114 to the exponent 1040 minus 100,000 times 0.00878114 equals, subtract 1 gives me 8011.8213 divided by, I'm going to put that into the bottom here, 1.00878814 to the exponent 1039 equals, multiplied by 1040 equals, subtract 100,000 equals 9066108.537. That's a number in the millions. That's encouraging. Put that in the bottom. Times 8011.8213 gives me something teeny tiny. And I'm going to take 0.00878814 and subtract the answer I just got. And my new guess is 0.0078976. And so this one would round to, wait a minute, 7897688. My significance digits start there, so 1, 2, 3. I need to keep that fourth one. It rounds up to a 7. Okay, there's my new guess. Okay, so I'm going to take this guess, I'm going to park it up here, and I'm going to speed it up so you can just watch me go through this until we eventually whittle this down to a value. So this precious machine stopped recording while I did all the rest of these without my knowledge. So I got through to iteration I, which means I started with A, and then did B, C, D, E, F, G, H, and I. That was 8 iterations, and I rendered down to this number so that I ended up having a repeat in this digit so that that thing is accurate up to 3 digits past my significant digit marker. So I have this number here, and if you remember how the formula worked, this was the rate paid on each payment. That means we were doing it 26 times a year. So to actually go out and get the posted interest rate, I'm going to have to take that number and multiply it by 26. If I do that, I get 0.161296 or something. So the interest rate I'm after is 16.130 if I round my third digit. So I guessed 13%. Chopped it up into this number and then ran it through 8 iterations of Newton's method, and it spat out 16.13%. So what that's telling me is that if I take $100 per pay and I put it in every pay cycle, so 26 times a year for 40 years, at that interest rate, then I will have precisely $10 million sitting in the bank on the day that I retire. So the next thing to do then is to go hunting for investment portfolios. So you go to the bank, and the number that they're going to quote you is a past yield, right? So they'll say this particular fund had an average past yield of 8%. Well, that's not enough. So if you find yourself one that has an average past yield of 20%, then it will be more than this, so that's good. But you've developed a target, right? This is the interest rate I need to make this happen. And you weren't able to do this calculation until you had Newton's method. So in sort of the summary of calculus that we've done so far, I now have the ability to find the max, mins, and slopes of any function anywhere. And I have the ability through the second derivative to find the curvature, points of inflection of any function anywhere, as long as they're solvable. And now that I have Newton's method, even if they're not solvable by algebra, I can approximate their values. So now that you have those two tools, the sets of derivatives that let you find an expression for intercepts, maximins, and points of inflections, you couple that with Newton's method, which allows you to approximate the value of any function set at 0, then you can now analyze any function ever. So there isn't a single thing in physics, economics, engineering, etc. that you can't use those two sets of tools to be able to analyze to find all of the optimal places, all the max-mins, all the places where it twists, right, with your points of inflection, and any x-intercepts for any function ever. And all this was cooked up by Isaac Newton and his friend Leibniz independently in around 1670. So that's like mind-blowing that this kind of math was cooked up 400 years ago. And it's allowed us to get away with all sorts of magic stuff like putting robots on Mars, or being able to build a stock market that is reasonably stable and keeps us all fed and clothed more or less, and are able to take rocks basically and turn them into robots that can crunch these numbers for us. This idea, this ability that Newton's method and calculus has given us, is sort of the fundamentals of engineering and everything, and it really has let us get away with magic. So I will leave you to the practice problems where you're going to evaluate some roots using Newton's method so that you can check that you're doing it properly. I'm going to ask you to find the x-intercepts of a particular function, and then I'm going to ask you to do a sketch of a function where you're going to need to use Newton's method to find the x-intercepts and the max-mins and the points of inflection. But you're real good at this now, so I believe in you. You can do it. Good luck.